All right, everybody. I think it's just about 10 o'clock. I think I'm going to go ahead and get started. It's good to see you all again. Welcome to a new week and a new month, actually. So we're starting into November. Um, Hopefully this time change thing didn't screw you up too badly. I'm a little screwed up actually from it. You might be able to tell it in my voice a little bit. Over the weekend, I didn't get my sleep schedule figured out very well. So I'm kind of struggling through a little bit today. Uh, we'll just take breaks as we need to. I will anyway, and just kind of pace ourselves. Um, we are in week 11, which means we only have 1/3 of the semester left to go. This week, as I sent you over the weekend, kind of a preview, we are going to go back to differential equations this week. If not today, then definitely by Thursday, which is going to be super exciting because that's kind of where the climax of Math 250B is. That's the whole reason that we're doing these subjects together, is so that we can use the linear algebra to help us to solve differential equations. So we just need to finish this last little bit on eigenvalues and eigenvectors, and we're going to be totally ready to do that. Okay. Just as a quick reminder, there is homework due tonight. I see a number of problems on the board over here. I'm going to be doing a number more of them, kind of blended in with the lecture a little bit. So hopefully that'll make life a little bit easier for you. As I said, I'm kind of on low energy. I don't know how long I'm going to last today. Technically, I do have office hours tonight, but by then I might be, I don't know, barely awake. We'll see. Hopefully I can make it through. But anyway, it'll be good to get as much of it done today during class as possible, so you don't have to worry about it so much later on. And I think it should be okay. Other than that, as soon as we're done with this homework, there is another one due on Friday, which will be more computational. I would say this homework assignment is a little more conceptual. The one for Friday will be more computational, and we're going to do lots of examples today to kind of show you what that might look like. So anyway, I think it's a pretty standard week, a pretty easy roadmap for us to follow here. And so I'm going to start, before I get to any of the homework, I'm going to start with kind of recapping where we left off last Thursday. It's been a few days, but I'm almost immediately going to be jumping into the homework questions because there's a lot of relevance to just even on the recap to what's in the homework problems. Okay, so let's see if we can talk this through. We're in chapter 7, which is about eigenvalues and eigenvectors. And the thing to keep in mind here, guys, is that the matrices in chapter 7 will all be square size. So n by n. And when you have a square matrix, then you have the potential to find eigenvalue eigenvector pairs. Okay, so the eigenvalue is lambda, the eigenvector is phi, and together they kind of go hand in hand. You can't have an eigenvalue without an eigenvector, and you cannot have an eigenvector without an eigenvalue. They always kind of come together as a package deal. And the most important equation in chapter 7 is the one that I put in the box right here, which is that when you have an eigenvector v, I'll draw a little picture for you here. If you have an eigenvector v, the matrix A, when it multiplies onto v, would need to simply stretch that vector by some scalar amount, which is what lambda represents. Okay, and remember, I mentioned this last time, lambda could be negative, lambda could be a fraction, so it's maybe not literally a stretch. It could be a shrink or it could be a flip over, but it's pointing in the same direction, right? That's the idea. And the other thing I wanted to say up here about this is that the eigenvectors are supposed to be non-zero. So I'm going to put this, I'm going to try to put wherever I'm helping with the homework, I'm going to put it in blue because right away, so we're in 7.1, I'm doing the 7.1 homework. There's a true false item B, I think I assigned. No, I'm sorry, it's part A. Part A of 7.1 says, so it's going to be false. Basically, it doesn't put in this b not equal to 0. What the true false item says is that an eigenvector is any vector v such that av equals lambda v. And that is false. It is any non-zero vector v. So for your true false, This is the point that they're trying to emphasize there. Eigenvectors have to be not zero. Okay. So that's the most important starting point for chapter 7, the most important equation. And then we went into a discussion about how to find the eigenvalues and eigenvectors of a matrix last time. And we got started on this. Basically, to find the eigenvalues, we solved this so-called characteristic equation. Notice that we are going to be using determinants here. Thanks to having a square matrix, that's all fine and good, right? I can take determinants of square matrices, but it's not just the matrix A, it's the matrix A with lambda subtracted off of the main diagonal of A. So this will be a matrix that has lambda in it on that main diagonal, and so you'll actually have an equation that you have to solve for lambda, okay? Now, as long as the matrix is fairly small, it shouldn't be too hard to solve that characteristic equation. But the bigger the matrix gets, the more different lambdas you could have, the higher the degree of this characteristic equation, and so on. So it gets hard. It can get hard to do this by hand if the matrix is big. 95% of the matrices I will ever ask you to work with are going to be 2x2s or 3x3s. Or the only exception to that is that if you have a triangular matrix, I think I'm going to come over and talk about this next. If you have a triangular matrix, it's easy to write down the eigenvalues. They are simply the numbers right on the main diagonal of A. So this is super good. I'm going to come over to warm up number 2, right? So this is really good. This is good for constructing examples. Of eigenvalues. So if you would like to write down a matrix and just know what its eigenvalues are off the top of your head, a great way to do it is to just make a triangular matrix and put those eigenvalues right down that main diagonal. Now, let's try and explain this and give the reason here. And I also would like to point out that this is the reason that 7.1 part, the true false item B, I think it is. Here's what B says. The eigenvalues of an upper or lower triangular matrix are the entries appearing on the main diagonal. That is true. That's exactly what this is saying. So this is a true item. And when you're giving a justification for your homework, because remember, I still see some people turning in homework that just says true or false with no reasons given. If you want to give a reason for this, you can just say, see warm up number 2 from November 4th lecture, right? Because that's exactly what I'm basically going to explain this fact right here. Why is it that for a triangular matrix, the eigenvalues are just the numbers right on the main diagonal? Well, here's the idea for the solution. If A is triangular, then so is A minus lambda I. Because all you're doing is subtracting lambda off of the main diagonal. You're not actually messing with any of the other numbers. So I'll just make a note here. Note that A minus lambda I is also triangular. And how do you take the determinant of a triangular matrix? Well, you just simply multiply the diagonal values, right? You remember that from chapter 3? By the way, it's triangular with entries A11 minus lambda, A22 minus lambda, and dot, 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 up to ANN minus lambda. Those are the values that will be on the main diagonal of A minus lambda I. It'll just be whatever the diagonal values of A were, and with the lambda now being subtracted from that diagonal, from all of those diagonal entries. Okay, so what is the determinant of this? Maybe I need to come over here to have a little bit more room. But what is the determinant of this, guys? Real easy. Real easy. we are going to just put it right here. The determinant of A minus lambda I is the product of these diagonal values. Right? So namely, A11 minus lambda times A22 minus lambda and times dot, 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 all the way along to A and N minus lambda, just like that. How do we find the eigenvalues of our matrix? Solve the characteristic equation. Take that determinant right there and set it equal to 0. So I'm going to set this one, guys, equal to 0 now. And I bet everybody can solve this equation for lambda. Either that's 0 or that's 0 or that's 0 or that's 0. One of those terms is 0. So this implies that lambda is equal to A11 or A22 or dot, 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 or possibly ANN. The lambdas are just the values on the main diagonal. And that's exactly what this exercise is showing us. Okay, so just as a quick example, like a specific example, the eigenvalues of, let's make a little matrix here. I'm going to make it a 4x4 just so it can be a little bit more interesting. Let's say 1, 0, 0, 0, and then 2, 3, 0, 0, and then 4, 5, 6, 0, and then 7, 8, 9, 10. If we write down that matrix, which is a 4x4 matrix, then what are the eigenvalues of this matrix, guys? Somebody want to tell me? 1, 3, 6, and 10. Absolutely. 1, 3, 6, and 10. So you can just read them off from the main diagonal of the matrix. That's the beauty of it. When the matrix is triangular, the eigenvalues are just sitting right on this main diagonal. Okay? That's good to know. That's a really helpful fact. Okay, so far so good? Questions there? So that justifies this item B, but if you just want to, in your homework, if you just want to reference warm up number 2 from today, that's fine. You can certainly just do that. Okay. By the way, another thing, so that of course the eigenvalues are not always this easy to find. The reason this was so easy is because the matrix was triangular. And so this fact allows me to do that. But normally, right, getting the lambdas right is a crucial step. It's actually something we have to really be careful about. We want to get it right. We want to get those lambdas right. So I've reminded you here in my recap also these fun facts about the eigenvalues that we can use to check them ordinarily. So when you add up all of your lambdas, they should add up to the trace of your matrix. Remember, the trace is just the sum of the diagonal values, right? So in this matrix here, the trace is 1 plus 3 plus 6 plus 10, which is 20, right? And if I add up my lambdas, they add up to 20. They're actually the exact same values in this case. And the other fun fact is that when you multiply your lambdas, it should equate with the determinant of your matrix. Okay, so I always like to check my lambdas against these fun facts because I really don't want to have the lambdas wrong when I'm trying to find the eigenvectors. So this is actually very important. I did not prove these facts last time. I teased you that you'll have to go take Math 307 to learn more details about it. But for the time being, we can at least take advantage of it when we're doing actual problems. Okay? So those are the fun facts about the eigenvalues. Okay. Now to find the eigenvectors, that's the other part of this process. Once we have the eigenvalues, then what we're going to be looking for is this so-called eigenspace E sub lambda, and it's just calculating a null space of A minus lambda I. Let's remember that this matrix A minus lambda I, right, it's not invertible because its determinant was 0. This is not an invertible matrix, so there's gonna be something in that null space. right? Only invertible matrices have trivial null spaces. So if it's a non-invertible matrix, you should be able to find an eigenvector here, a non-zero vector, right, that's in this null space. Okay, so these three boxes on the board here that I've put around these things, these are the highlights. These are the absolute key ideas. Okay. So far, so good? Okay, well, I have another warm-up problem. I guess I'm doing them out of order here. This one is also a nice little observation. If you have a matrix that satisfies some equation, so I actually literally just made this up, a squared minus 3a plus 8i equals 0. It turns out that the eigenvalues of a matrix will always solve exactly the same equations that the matrix itself solves. Isn't that kind of interesting? So you have this polynomial here, p of x, which is basically x squared minus 3x plus 8. And if you plug the matrix A into this polynomial, you get 0. Well, if you take any of the eigenvalues of A and plug those in, you'll also get 0. It's kind of interesting that it works that way, but it absolutely does. Let's try to show this one as well, okay? So for the solution here, does everybody understand what it's saying? This is a matrix equation up here. And it turns out that this is a scalar equation, which is satisfied, exactly the same scalar equation is satisfied by the eigenvalues of the matrix. It's a famous result. It's actually a pretty nice fact here. And I'm gonna show it to you right now. Okay. And by the way, there is a true false item also about this. So if we look at a 7.1 on the true false part I, now I have to say that the one that's on part I is a little different. It's not this exact equation. I think what they give you is a cubed, and then they say show that lambda cubed would be 0, but it's the same idea. So I'm gonna do this one for you, and then you'll have to just tweak it or modify it in order to justify. This one is also going to be true. Okay, so let's see if we can justify this. Okay. So this is the given information right here. But in the original given information, I don't see anything about eigenvalues and eigenvectors. They tell us that lambda is an eigenvalue of A. So you know what I'm going to do first, guys? If I have an eigenvalue of A, I'm going to go back to the most important equation in chapter 7, especially for theoretical ideas, and I'm going to write it down. So we have AV equals lambda V, where V is a non-zero vector. I'm just emphasizing again that V is not 0 here. Now, one thing that I've seen people do with an equation like this, can I get out my red pen? The red pen means don't do this. The red pen means, so don't write this down, but I almost always will see somebody try to do something like this. They see the a squared in the problem and they're like, well, I should square this to get a squared in there. But what we have to realize here, guys, is that you cannot square a vector. So V is a vector and AV is a vector, and it doesn't make sense to square that vector. We actually cannot do that. It just doesn't make any sense. So I put that in red and I'm crossing it off. Okay, get it out of your mind. Every exam I give in this class, there's always somebody who tries to do this. So don't let it be you when we get around to another exam. Instead, the better thing to do here, instead of squaring both sides, the better thing to do is to actually just multiply this equation by A on the left of both sides. So what we can do is we can go ahead and write this as A times AV equals A times lambda V. So that is okay. That we can do. And what we end up with is we end up with A squared V on the left. So it's just A times V. And on the right, I can pull the scalar, so lambda is just a number, guys. I'm gonna pull it into the front. And after I pull it into the front, I put the A with the V again, and then you probably realize that the AV that I've created can be changed also to lambda V again. And so this actually just becomes lambda squared V. Okay, so A squared V is equal to lambda squared V. By the way, I have another question for you. Is it fair to just cancel, is it okay to just cancel the V from both sides? Right here? Or could I do that right here? Would it be correct to say that A squared is equal to lambda squared? I mean, they aren't even the same kind of creature, right? A is a matrix, lambda is a number. So you would never want to try to tell me that A is equal to lambda by canceling the vector. I know it's tempting, especially when you see V is not zero. Like, oh, I want to cancel the V. You can't do that. You cannot actually cancel the V there. Okay, so how do we finish this little proof then? So on the one that's in the homework where you have the true false, you actually have to do the third power of A. I'll leave that to you, but it works out the same way. You get A cubed V equals lambda cubed V. But what I want to do here is the following. So let's just keep this little argument going. What I'm going to do is I'm actually going to take A squared minus 3A plus 8I, the whole thing, and I'm going to apply it to V. This whole original equation. Now I know that that is supposed to equal to 0 times V. Because we were told that A squared minus 3A plus 8I is equal to 0. And of course, 0 times V is just 0. That I know. Okay, stop me if there's anything here that's unclear. You are probably going to get asked to do something like this at some point in the future. So here's my matrix times V equals 0 times V. I'm literally just taking this given information and I'm applying it to V. All right, well, let's split up this left side. It's A squared V minus 3AV plus 8IV, all equal to 0 now. But A squared V, we just worked it out, it's lambda squared V. And then we have minus 3 times AV, but I can replace AV with lambda V. And then I can just drop the identity matrix because that's like multiplying by 1. So I just get 8V, and that equals to 0. Now let's factor the V out. So I'm going to get some parentheses going here, guys. I'm going to factor out that quadratic formula for lambda and put the V on the end of it. And what do I have here, guys? What do I have here? I have my non-zero vector V being scalar multiplied by something and ending up giving me 0. So it's like, well, then what would the scalar have to have been? 0. Exactly. That's what you're trying to show. Show that that scalar is 0. This is exactly what we can say now. We have V is not 0, but it's being scalar multiplied by something and it's becoming 0. So that scalar must have been 0, right? So thus, lambda squared minus 3 lambda plus 8 is equal to 0. That is how we finish this little proof. Okay, so that justifies that this is a true statement. Okay, how does everybody feel about all that? So far, so good? Okay, great. Well, I tell you what, while we're on the subject of kind of doing these conceptual questions and kind of doing some of the homework, I think I'm going to turn to a couple of the problems that are in that homework there and work them out for you right now, okay? So we're still doing the 7.1 problems. We'll go back to 6.4 later today when it's a little better timing. Right now, I want to stick with 7.1. So let's do a couple more of these homework problems. But before I do that, are there any questions here? Guys, I could have changed this to anything I want. There's nothing special about a squared minus 3a plus 8i. I could have made any polynomial equation in A, and the same equation would be true for any of its lambdas. Adrian?
Replace A with lambda and just the value of it.
That's basically what this is showing. That you can basically replace the A with the lambda, which is kind of how this box equation is suggesting as well. Yeah, absolutely true. Okay, let's take a look at a couple of things off of the homework. I'll start with, so this is 7.1. Let's look at number 41 together. These are all, the 7.1 homework is mostly conceptual questions for today, guys. So that's what we're looking at here. So let's let A be an n by n invertible matrix. Okay, and it says, if lambda is an eigenvalue of A, then show that 1 over lambda is an eigenvalue of A inverse. This is problem 41 for the homework that's due tonight. When I see the lambda on the bottom of a fraction, I always have a little nervousness about that. Could lambda have been 0? If lambda was 0, then this wouldn't make sense to have 1 over lambda there. Does anybody have any thoughts about whether the lambda could be 0 here or not? And if I can give you a hint, take a look at the fun facts about the eigenvalues. There's something there that would tell you that if A is invertible, right? If A is invertible, then what can you tell me, Kenny?
The determinant of A cannot equal 0.
Right, so for an invertible matrix, this determinant here would not be 0. So could any of these lambdas be 0? Never could happen, right? So that means that we are pretty safe in knowing this isn't really part of the full solution yet, but I'm just gonna make a note that lambda is not equal to 0 since A is invertible. And we could just add for our notes here, see fun fact number 2. Is that what I called it? Yeah, fun fact number 2, that kind of explains it. So if A is invertible, then your lambda is not going to be 0. Okay, so that's just a little bit of a clarification at the beginning, just so that this actually does make sense. Now let's actually try to solve the problem. It says, suppose that lambda is an eigenvalue of A. Well, that's the same way this started off. If lambda is an eigenvalue of A, and the very first thing I wrote down here was this $1 million equation, the most important equation in chapter 7. I'm going to start with that over here as well. So we know that AV equals lambda V for some V not equal to 0. You might notice that the V is actually never mentioned in the question. Right? The question only talks about the matrix and the eigenvalue, but we know that eigenvalues and eigenvectors go hand in hand. So if I have an eigenvalue, then there has to be some vector V that is corresponding to that. And so it shows up right here in this equation. So AV is equal to lambda V. Okay, so this is what I've got. Does anybody want to suggest what I could do? This is the only thing I've got to work with. Anything I can do. We're not going to square both sides, I know that. But is there something that we could do here? In this problem, we took the equation and we multiplied on the left by A. Right? That's kind of how we started off. Not sure that's what we would want to do here, but maybe we could do something similar. Same kind of idea. Anybody want to try it? Don't worry if it's wrong, guys. We're just learning. It's just brand new material. Of course, we aren't just flying blind here, guys. We actually are trying to show something. Let's look at what that is. We're trying to show something about 1 over lambda, and we're trying to show something about A inverse. Neither of which is showing up in my box so far. So I have to bring those things into my work. I don't see 1 over lambda, and I don't see A inverse right here. Is there a way to bring them into this?
Multiply by A inverse.
Absolutely. So if we were multiplying by A right here, it makes sense maybe on this problem. Let's try multiplying through by A inverse. Let's check it out. So we have an A inverse that we can use. So I'm going to use it. A inverse times A times V equals A inverse times lambda times V. So it would be something kind of like that. So real quick, can you remind me what is A inverse times A? It's not technically 1, it's the matrix that acts like a 1 though, which is the identity matrix. The identity matrix times V is actually just V. So we can just write that as V. I'm also going to do what I did before and pull that lambda out in front, just like I did on the other example a minute ago. So I'll put the lambda in front of the A inverse V. Okay, let me come over here. What do you suppose I'm going to want to do next? And again, keep in mind, this is where we're going. I now have an A inverse in front of me, but I don't see a 1 over lambda yet. How can I make 1 over lambda happen, Jose? Absolutely, we can just flip this lambda to the denominator of the other side, right? So that's exactly right. So I'm going to go ahead and write A inverse times V, but I'm going to put 1 over lambda times V on the other side of the equation. So I'm flipping the lambda to the denominator on the other side of the equal sign. You see that? And guys, when you look at this, this is the $1 million equation again, but for A inverse and for 1 over lambda. It's the same equation that's in this box, except we've replaced A with A inverse, and we've replaced lambda with 1 over lambda. Otherwise, it's exactly the same thing. So 1 over lambda is an eigenvalue of A inverse. That's it. That's how it works. Nice. And notice that the corresponding eigenvector is still V. That actually didn't change. So although we replaced A with A inverse and we replaced lambda with 1 over lambda, the V, the eigenvector, did not change. It's the same associated eigenvector, actually. So that's good to just observe. So far, so good? You poor guys, you had a rough weekend with the extra hour of sleep. Everybody's a little groggy, and I come in here and do a whole bunch of theoretical problems to start off class today. I do apologize for that, but the nice thing about these is the write-ups are pretty short. They're pretty short. Let's look at 42B. Somebody put that on the board as well. So this is also from the homework in 7.1. What does this say? This one says, assume that A is n by n and B is n by n, and V is an eigenvector of A corresponding to lambda, and also an eigenvector of B corresponding to, and they use this other Greek letter, it's called mu. Mu is how it's spelled. It looks kind of like a stretched out U. And then what they ask you to do is show that V is also an eigenvector of A plus B. Okay. So you guys see how much writing that took to write down the question? To write down the answer is going to take less than half of that, probably a quarter of that, right? So much less than that. If I want to show that something is an eigenvector of something, that really just means it has to satisfy this equation, doesn't it? Aren't I just going to, so this is a one-liner, guys. Okay, don't break a sweat on this one. You're just going to take A plus B, that's the matrix that they're asking you about. You're going to check that V is actually an eigenvector of it by calculating what this is equal to. Now, we all know that matrix algebra applies here. I can split this into two parts just using the distributive law, right? I can write that as AV plus BV. But what does AV equal? Lambda V, right? Lambda V. So AV is lambda V. And what does BV equal? Mu V, right? We have this other eigenvalue, mu. It's also a scalar. Mu V. So A plus B times V can be broken up into two parts. V is an eigenvector of A and an eigenvector of B, but with different scalars, different eigenvalues. And what am I going to do from here? Factor it. Absolutely. Let's just factor out. It's good to keep that V on the right, put the scalar in front of it. It's just lambda plus mu. Guys, that is literally our $1 million equation again, but with A plus B where the A was, and lambda plus mu where the lambda was, right? So this checks it. That's all you have there. And in case somebody asks you, well, if you have an eigenvector, there has to be a corresponding eigenvalue. I think the question actually does ask you for this, but it's just sitting right there for you. It's just lambda plus mu. Right. So if you have two different matrices and you have a vector that is an eigenvector of both of them, well, then you can add the matrices together and that same eigenvector will still be an eigenvector. And the corresponding eigenvalue is obtained by just adding up the individual eigenvalues. Okay, so nothing too crazy here, guys. Just kind of do the only thing you can do, which is play with this equation. Why did I assign all of these problems, right? It's really because these problems that we've been looking at in the warm-ups force us to not forget about the most important equation in chapter 7. For the rest of today's lecture, this is going to end up being in the background. We're going to be doing more of these determinants and null spaces, but I don't like people to forget about where this all started from, because this is the whole motivation behind eigenvalues and eigenvectors. So that's why I assigned a couple of problems like this, just so everybody can kind of practice it a little bit. Okay. So far, so good? Questions? All right. Well, I'm on a roll. There's only one problem left in 7.1 on the board over there. We might as well just do it now. I think it's fine to hit number 9 from the homework. This one's a little bit different, and so you'll see this is a little bit challenging. On number 9, I'm just going to abbreviate the question a little bit. They tell you that they're thinking about a linear transformation from R2 to R2. Now, this goes back to chapter 6 when we're talking about linear transformations. And in this case, remember that there will always be a matrix that represents this transformation. It is a so-called matrix transformation. And they give you the matrix here on problem 9. It's going to be the matrix 0, 1, and 1, 0. Okay, and so what they tell you that the effect of this matrix is to reflect the vectors across the line y equals x. So before I actually go on with the problem any further, I just want to make sure everybody kind of understands the picture that's behind this thing. The line y equals x is right here. So I'm just going to kind of draw that in. That's y equals x. What the book is saying is that if you start with some vector over here, let's just make up a specific example, let's say 4, 1. What this says is that the effect is to reflect the vector across the line y equals x. Well, if I reflect this vector across the line y equals x, it's going to go up here and become the vector 1, 4. So this is like your vector v, and then this becomes your vector AV. That's the idea. So I mean, you can see it, can't you? If I plug in coordinates x and y out of R2 here, and I do this matrix multiplication. Okay, watch this with me. If I do this matrix multiplication, 0 plus y goes first, and then x plus 0 goes second. Look what happened with the two slots. The xy vector that you plugged in got flip-flopped into the vector yx. So that's what we're seeing here. The vector 4, 1 got flipped to the vector 1, 4. The two slots traded places, right? So I still have not read what the question is asking. I'm just trying to make sure people kind of have a picture in their head about what's going on here. This is a matrix transformation with a 2 by 2 matrix that has this kind of an effect, right? So if I plugged in the vector, 9, 1, right? Then the reflected version of that would go up here. It would be 1, 9, and so on. So I have a question. So then what they're going to ask us is find the eigenvalues and eigenvectors of A. Find the eigenvalues and eigenvectors of A. So I've got some vectors already on the board here. Would the vector 4, 1 be an eigenvector? Remember that the visual of eigenvectors is what's in blue right here, guys. An eigenvector is one where when you start with that vector and you multiply it by A, it stretches it. It stretches it in the same direction or possibly flips it over, but it does not turn that vector. So would you say that this vector 4, 1 is an eigenvector if it ends up pointing up to 1, 4? I don't think so. This is a rotation, right? The vector has been rotated. Same thing with 9, 1 and 1, 9. Those are not scalar multiples of each other either, so I don't have any eigenvectors there either. So the question is, where are the eigenvalues and eigenvectors? Or what are the eigenvalues and what vectors would they be that would not get rotated, but would only be stretched? Holman, do you think you have an idea? Remember, eigenvectors cannot be 0. So we cannot use the 0 vector as an eigenvector. Trevor?
Would it be along the line of y equals x?
Oh, what about that? What if my vector was right here, right? Then when I flip that vector along the line y equals x, where does it go? Doesn't it just stay in the same place? It's just fixed there. If it's on the axis of the reflection, then it doesn't move when you do the reflection, right? This vector would be the same exact vector as AV. That blue vector that I drew right on the line y equals x. And you can try it here if I plug in 1, 1. Or if I plug in 5, 5. As long as it's something that was on the line y equals x, then when I switch the x and the y, nothing happens. Right? And so what would be that eigenvalue, by the way? what would be this eigenvalue that goes with this blue visual that I have here? So now let's get to the solution. The eigenvalue would be 1, right? Let's call that lambda. The eigenvalue would be lambda equals 1 because AV is equal to 1V. The lambda value is just 1. That vector is actually not being stretched or shrunk. It's just staying exactly as is. So there is an eigenvalue of 1, and then the eigenvectors would just be, actually, it's just going to be any vector that's on that dotted line. So it's just going to be any vector of the form AA, where A is not 0. I can't use the 0 vector to figure that out. But that is one answer. Now, is that going to be the only eigenvalue and eigenvector? Let's not forget our fun facts about the eigenvalues. All of the eigenvalues that you have in total have to add up to the trace of the matrix. What is the trace of this matrix? The main diagonal, when I add it up, I get 0, right? So if 1 is an eigenvalue, then in order for my fun fact to be true, what would be another lambda that we would be expecting? -1. Absolutely true, right? Because the two lambdas should add up to 0, if you believe my fun facts. So this would be a scenario where AV is equal to -V, right? If the lambda value is -1, then AV should equal negative of V. Can anybody tell me where on this picture I could draw a vector such that after I reflect it across that dotted line, it becomes the negative of what it was before? Can you see it? Let me make a vector right here. If I pick that vector right there, and I'm choosing it to be at a right angle here, guys. What happens when you take this vector and you reflect it along that dotted line? Doesn't it just flip it over? Like that? And that's literally the negative of the vector you started with. Yeah, so that's exactly what it is. These vectors would all be along the line y equals -x. So I could draw this as, say, -a and a, where a does not equal 0 again. So those are going to be the eigenvectors in that case. And that's all you'll have. For a 2 by 2 matrix, you're only going to get 2 lambdas. But that's the whole story. I really like this example because it brings the geometry into the problem. Guys, we didn't really need to do the geometry if we didn't want to. I could have just taken this matrix and I could have just done my characteristic equation with it. I could have just subtracted lambda off of the main diagonal. Watch this. I could just subtract the lambda off of the main diagonal. When I do this little 2 by 2 determinant, I get lambda squared -1. Well, of course, when I set that equal to 0, I will get 2 values of lambda, which are exactly the ones we found here. So you can do this all without the picture, but it's nice to have the picture so you kind of see a visual of what's really going on. That's why I like this problem, is it shows kind of what this is all about. It's easy to get lost in the weeds of the calculations here. But I like people to remember what the concept is of eigenvalues and eigenvectors. And a problem like number 9 really helps us to see that in front of us. Yeah. Okay. Everybody good? So far, so good? All right, so that's about it for 7.1 on the homework. We'll talk about 6.4 a little bit later today. But while I am on a roll with chapter 7, I'm going to keep going a little bit further into the material. You guys okay if we just go for a little longer before we take a break? Okay, let's just go a little bit further here. So far, I've been doing all the conceptual recap and all that, I wanna get it back into the crunching of the numbers. So let's do that, and I need to find my little example from last class. Okay, so let's get back to taking some notes again. So these are gonna now be some new notes. Although I actually would like to recall the example that I did on Thursday last week, which was October 30th. So I'm gonna put this back up here again. There was a 3x3 matrix that I gave you. And it was this matrix right here. So 3, 0, and 0. And then 0 and 2 and -1. And then 1 and -1 and 2. So we looked at this example last time. And I am just gonna summarize what we found in this example. We found the lambda values are 3, 3, and 1. Notice that the trace of this matrix is 7. And if I add up these 3 lambdas, I do get 7. So that confirms that. Also, the determinant of this matrix, if I calculated it, it would be 9. And if I multiply my lambdas, I get 9. See, I always like to check that I've got my lambdas correct. And then what I did last Thursday is I calculated the bases for the eigenspaces. So there was a basis for E sub lambda equals 3. And I'm just gonna remind you, we did this already, I'm just putting it back into the notes again. And what we got was 0, -1, and 1. And then we also took the other eigenvalue and we did a basis for that eigenspace as well. Okay, so I won't review this whole calculation again, because we're gonna just do a new example today. So this one came out to be 0 and 1 and 1. All of that involves doing these null spaces, right? So you take your eigenvalues and you do all these null spaces for both of them. Remember, I said last time that we are gonna get really intimate with null spaces in this chapter. So those were the details of what we did on the example last time. And I wanna have that up on the board because I'm gonna do a new example now. And I would like us to compare these examples, okay? You ready for this? Let's do a new example. This one we have not done before. Let's find bases for the eigenspaces of, and just so we don't get it confused with the matrix A, I'm gonna call this one B instead. Okay, but it's also gonna be a 3x3 matrix, 2, -5, and 5. And then 0, 3, and then -1. And then 0 and -1 and 3, like so. Find bases for these eigenspaces. Okay, so the way that we do this is we start by using our characteristic equation to try to find the eigenvalues. Okay, so let's just remember how that works. So for the solution here, I have to take the determinant of, give yourself plenty of room, guys, because we're gonna have a lambda in this matrix now. I'm going to subtract lambda off of the main diagonal of this matrix. So 2 minus lambda, -5 and 5. And then in the second row, I have 0, and then 3 minus lambda and -1. And then 0 and -1, and then 3 minus lambda. Awesome. And what I need from somebody is to tell me how to do this determinant. Would you have a suggestion? I would use cofactor expansion. Remember, guys, on Thursday last week, I mentioned that as soon as there are lambdas inside of this matrix, the arrow method is not so favorable for solving for lambda. It's more doable, in this case especially, when I see this column of zeros, that I expand, I do cofactor expansion. In this case, I'm gonna do column 1. So I'm gonna expand on column 1. I have a 2 minus lambda already in the upper left corner. When I cross off that row and column, it leaves me with this little 2 by 2 determinant in the lower right corner, which is 3 minus lambda times 3 minus lambda, all minus 1. And the idea here, guys, is that we are trying to get this factored. I don't want to multiply it out, right? Multiplying it out is kind of going in the wrong direction. I want to get it factored. So I actually very much like the fact that 2 minus lambda is already factored into the front. Because what's left in the brackets is only going to be a quadratic equation. That can't be that bad, right? So this little bracketed piece, if I multiply just that part out, I'm not going to multiply out the 2 minus lambda, just the part in the brackets, I see a lambda squared minus a 6 lambda and then a plus 8. And that's a quadratic equation, and I never get too scared of those because I've always got the quadratic formula to find the roots. In this case, I don't need the quadratic formula because this actually factors nicely. But even if it doesn't factor nicely, we could factor it. But I'll just go ahead and tell you that it factors as lambda minus 2 times lambda minus 4. And this is the way you want to get your characteristic equation. You want to get it totally factored out. Factor after factor after factor. And then we set that, as always, we're going to set that equal to 0. And so what are my lambda values?
2, 2, 4.
One more time.
2, 2, 4.
2 and 2 and 4. Exactly. Exactly. I mentioned this last week. I'm going to re-emphasize it right now, guys. Make sure you write down repeats of the eigenvalues. If they come up more than once, write them down more than once. Okay, so that's going to turn out to be important. While I'm erasing, you guys could check my fun facts, figure out whether these have the right, if they add up to the right amount and whether they multiply to the right amount. The trace should be 8, I believe, and then the determinant should be 16. And you can kind of look at the matrix B and check that. Okay? Great, let's do our corresponding eigenvectors now that we have our eigenvalues. So let's take lambda equals 2. And for each of these lambdas, now I have to calculate this null space, right, to get my eigenvectors. So I'm going to be calculating a null space here of the matrix that I get when I subtract 2 off of the main diagonal of B. So just the diagonal entries only. So I'm going to get 0, -5, and 5. And then I'm going to get 0, and 1, and -1. And then I'm going to get 0, and -1, and 1. So I have subtracted. If anybody's lost, be sure to let me know so I can clear it up. All I did was subtract 2 from the diagonal values only. Everything else is recopied the same. In addition to your fun facts, the other thing that you can confirm your eigenvalues with is that this matrix, when you actually write it down, it should never be invertible. If you're looking at this and you're feeling like it's invertible, that's a red flag. That would tell me that there's something wrong with my eigenvalue. But I can kind of see that if I have a column of zeros, it's definitely not invertible. And in fact, we know that if we did the EROs here, we would be able to cross off at least one row. But actually, if you look at this, all 3 rows are multiples of the same row. So you actually could cross off 2 of them. And I kind of like to have my pivot as a 1. So I'm gonna cross off 2 rows here. People sometimes they'll ask me, well, how do I know how many rows I can cross off? The answer is I don't always know how many I can cross off, but I have to be able to cross off at least 1. In this case, we actually did better than that. So if I lay out my XYZ variables for this null space, I can see that Z is free and X is also free. I'm going to use R and T for those variables. And if I read off of my middle equation here, the middle equation tells me that Y minus Z is 0. Okay, y minus z is equal to 0, that means y and z are the same. If y minus z is 0, then y would have to also be t. Okay, and so let's get our basis for the eigenspace E sub lambda equals to 2. And what I want you to notice here, guys, is that the R factors out and gives me a 1, 0, 0. And then the T factors out and gives me a 0, 1, 1. That's right. Okay, so there's your first eigenspace. So when you put this into a vector, right, you make this into a single vector, when you bust out the variables, you'll get 1, 0, 0 as well as 0, 1, 1. So far, so good. What about my other eigenvalue? Let's do that one really quickly. Lambda equals 4. That's my other lambda. And so again, we're going to have a null space of something here. I'm going to subtract 4 from the main diagonal of the matrix B. So I subtract 4, I'll get -2, -5, 5. And then 0, -1, -1. And then 0, -1, and -1. And again, this matrix cannot be invertible. And if it is invertible, something's wrong. But I can see that the second and third rows are the same. And I'm going to cross off the repetition of that third row. I'll circle pivot positions here. And I kind of have 2 of those. So I can kind of do that. Let's set up the XYZ like so. And again, remember guys, when you're doing null spaces, all of these equations are set equal to 0. So this second row is really just telling me that -y minus z adds up to 0. So if z is a free variable, I'll call it t, then I can see that y has to cancel out the z, because essentially y plus z adds up to 0. So y and z are negatives of each other. And now I have to take this first equation, and this one's a little bit of a pain. I have to write down, I'm going to go ahead and write it out here, guys. I have to solve for x in this first equation that the first row gives me. But I already know that y is equal to -t, so I'll replace y with -t. And I already know that z is equal to t, so I'll replace z with t. And my goal is to solve for x. And when you do that, you should get 5t. X equals 5t. I'm going a little bit quick with these very sort of basic computational aspects here, but this is the XYZ. You're going to bust out the variable here, and we can write down a basis again. A basis for the eigenspace corresponding to lambda equals 4. And again, guys, on the homework where it says find eigenvalues and eigenvectors, it's good enough for me. I would actually prefer it if you would just write down a basis for each eigenspace, exactly what I'm doing right now. This is going to be for Friday's homework, and a lot of what you're going to be doing, okay? So I'll bust out this t so I can get my actual basis vector, which would be 5, -1, and 1. Those are my 2 eigenspaces in this case. Everybody with me? Any questions on that? Jakob, yes.
I mean, just from noticing, I know with the multiplicity of a number, it comes out with like two vectors in the bases.
Would you like to just take my notes and just pick up right where I left off? You are exactly seeing the next point we're gonna make. Yeah, there is something going on here, guys. And I have both of these examples up here at the same time, A and B. I want you to notice, did you notice on both of these examples that there was an eigenvalue that was repeated twice? Right, same thing happened here, but there's a difference. There's a difference between these 2 examples. This is what Jakob's getting at. And that is that in the first example, the eigenvalue lambda equals 3 was repeated twice. It had a weight, or as Jakob says, a multiplicity of 2, right? And yet only produced 1 eigenvector. In other words, this eigenvalue did not pull its weight. It only produced a one-dimensional eigenspace, whereas the eigenvalue shows up with a weight of 2. On the second example, we also had an eigenvalue that had a weight of 2, but this time that eigenvalue did pull its weight. The eigenspace gave us 2 basis vectors. Did you notice that? Right, here you have one eigenvalue twice and then a separate one. And when we looked at the bases, there's 2 things here and 1 thing here. That is absolutely what I was hoping somebody might notice. And there is something very important about this. So I'm going to write a quick definition down, okay? So we're gonna add this to our notes. I think I'm gonna come back over here, finally have to erase this recap. And I want to define a defective matrix, which is what A is, and a non-defective matrix, which is what B is. Okay, let's do it. Let's do it, guys. Woo. Yeah, so here's a definition based on these 2 examples. An n by n matrix. Now let me stop right there. On both of these examples, n was 3. 3 by 3 matrices, right? An n by n matrix with n linearly independent eigenvectors. Well, let's see, how many eigenvectors did we get in the first matrix? 2, only 2, right? These 2. Whereas in the second matrix, we got 3. We got 3, so 2 versus 3. So if my n by n matrix actually produces n linearly independent eigenvectors, this is called a non-defective. Or in other words, a diagonalizable, another fancy word, matrix. I got very confused as a student. I saw both of these words in my notes and I was like, wait a minute, what's the difference between diagonalizable and non-defective? The answer is there's no difference. It's just 2 different words for the same thing. It's 2 different words for the same thing. So if a matrix produces n linearly independent eigenvectors, it will be non-defective. Otherwise, the matrix is defective. Okay, so every matrix is either defective or not defective, depending on this situation. Okay, and so in the examples above, the matrix A was defective. That's because we only got 2 eigenvectors. Let me write that down. So n was equal to 3, but we got 2 eigenvectors total. When we went through all of our different lambdas, we only got 1 here and we got 1 here. We did not get 3 eigenvectors, we only got 2. However, B is non-defective. And again, n equals 3, and we got 3 eigenvectors out of all of those bases that we created over there. Now, there's another way to say what a non-defective matrix is. And I want you guys to actually be thinking about it this way. Because this is maybe a little bit easier way to think about it. A matrix is non-defective if and only if. So I'm gonna give you a different way of thinking about this. A non-defective matrix is one, guys, where every eigenvalue, quote unquote, pulls its weight. That did not happen here. This matrix in example A, we have an eigenvalue that had a weight of 2 and only created one eigenvector. But in the matrix B, every eigenvector, if I look at how many times everything repeated, the weight of the eigenvalue matches the dimension of the eigenspace. The eigenvalues are all pulling their weight. Let's write this down yet one more way. If we look at the dimension of each of these E sub lambdas. So when I say every eigenvalue pulls its weight, I mean the dimension of each eigenspace should match what I'm gonna write as M sub lambda. Now I need to explain what that is. M sub lambda, let me just add that up here. So where M sub lambda is the multiplicity of lambda. Meaning the number of times lambda is a root of the characteristic equation. That's my point. Okay. Right. By the way, as soon, I should add a little bit more here. This is for each lambda. For each lambda. Some of you might be wondering. You might be wondering to yourself, well, if one of the eigenvalues fails to pull its weight, like we saw in this example, which I just erased. If one of the eigenvalues pulls its weight, the skeptic out there is going to say to me, well, maybe one of the other eigenvalues could over-pull its weight and make up for that. It actually is not possible. No eigenvalue will ever over-pull its weight. So this eigenvalue of 2 and 2 will never be able to give you more than just 2 eigenvectors. The eigenvalue of 4 will never be able to give you more than 1 eigenvector. So as soon as one of the eigenvalues fails to pull its weight, it's game over. You cannot make up for that by finding a different eigenvalue to, oh, sorry, I'm getting a little crazy. You cannot find another eigenvalue that's gonna like make up the difference. Let's just keep people awake. I'm gonna start tossing markers at people. Yeah, so anyway, that's the idea. That's the idea. So no eigenvalue can ever overpull its weight. That's a fact really that I don't want to take the time to kind of explain right now, but you'll notice it on the examples. By the way, so if I give you this matrix, we're going to take a break, but if I give you this matrix and I ask you, is it defective or not? The first thing you're going to do is figure out your lambdas. And then if there's no repeat lambdas, if there were no repeats, you already know that it's not defective because every eigenvalue will pull a weight of 1. You have to get an eigenvalue, an eigenvector for every eigenvalue. So if there's no repeats on your lambdas, it's good news already. You don't even have to go any further. Keep that in mind on the homework for Friday. There's a couple of problems where it just says, is this defective or not? And once you realize that there's no repeated eigenvalues, you can stop. You can just say, yep, it's not defective. But if there are repeats, like there was here, that does not mean that the matrix is defective automatically. And in fact, this one was not defective. So what you need to do is check to see whether every eigenvalue pulls its weight. Now this one for sure will, because it's only got a weight of 1, a multiplicity of 1. But the other one, which was repeated, may or may not pull its weight. I had to do this null space up here to come up with two vectors. What I'm trying to get around to saying, in the long way of saying it, is when you have repeat lambdas, do the repeats first. Whichever lambdas repeat are the ones that might fail to pull their weight. So I would recommend, if you just don't want to waste time, it's best to do the repeat eigenvalues first and then do the other ones. Because if the first eigenvalue, if the repeated eigenvalue doesn't pull its weight, it's already game over. It's not going to be a non-defective matrix. You guys following? Okay. Well, I've been talking for a long time. I probably need to rest my voice for 10 minutes. Let's take a little short break here and then we'll come back and do maybe one more example. And then I'm going to hit those 6.4 homework problems. 10 minutes, we'll start back up again.
You remember that? Go to 10th mail. You get to second 10 minutes. The first thing. Copy the new one. Copy. Yeah, go back. And then sign it whatever account you're in. Oh, okay, so sign it. Email. That's the passwords. You fill password. Yeah. You start. Just make some shit. 6 seconds. Yeah, I wouldn't say all these small special this like this maybe we can call this there. But when you go here, like if it says that's it, you just flip it. And then this is like the inbox of that thing. 070. All right, and then campus. And then you set. You can grab it right after this. Yeah. Same. Well, are we going to this one first? After. I'm gonna get Panda, then go to this. So. Class of 23. We'll see. Class of 23. Let's see. And that's I'm gonna get a question. And you can do whatever you want. Yeah, it works on anything. It works on anything in there. So let's you can get a Pokeball and stick. Okay. No, I'm sure. Everybody else is ready to go. I might get chicken. That's all I want. All I want is you. That's nice food. Okay. Is the spicy or chicken always only this You don't like rice? Cheese.
Oh.
So you're Hispanic. Are you Asian? What are you?
My ancestry says everything. Steam drains.
You're steam drinks.
Your steam drain.
You're cute.
And then what is it?
It's so sad. One day we're gonna be honest.
Like, well, the small percentage. So do that. With the panda having to express what. Do I need to put it on?
Yeah, that's just. It doesn't like a society. Mhm. If you pay, you pay 75 more cents. Yeah, another option. I do that, so.
Oh, it gotta be that. I'm gonna get it anyways though. Save it for later, so.
Why would I pick out? Who's not?
I know.
Time change was the bad one. What do you mean, like the, I'll use it now. I didn't know, this is a good one. The game.
This is how like normal.
And then here, this is a good one. So you just order what you need here. Yeah. Then you just pick it up. You pick it up, it's still pick up.
Longer release one.
Yeah.
But we'll just pick when we.
Oh, sorry, bro.
You're good.
Is it still going?
Yeah, I just leave it on. I usually don't turn it
What's
on.
up, vlog? What? Yeah. We'll be on YouTube. My name is Keone Guerrero.
One of those. My mom was like,
Yeah, reasonably. She said,
I know.
I get
You get pop.
Mm-hmm. Cause one
I
time,
love a good Popeyes biscuit, bro.
dude, one time they had this crazy deal for like a week. And me and Zach went on this San Francisco and they had started. And they had 12 tenders for $12. And
So you can offer that.
no, I ate it all in City. I was so big, bro.
Years.
Is Elliot here?
Dude,
Caitlin?
what? Do it again. Wait, no, bro, no, that's a promo code. Huzzah.
All right, guys, maybe we can go ahead. I think I was the only one who took a break. A couple people stepped outside. I assume you guys like taking a little break in the class, like a little mental break, even if you don't actually stand up. It's like,
It's nice.
it's nice to not, you have to check your phones. And see
Yeah, I have
what's
to.
going on in the world, all that kind of stuff. I get that. I get that. I do that too. Any questions, guys, about anything we've said in the first part of our class today? This idea of a non-defective matrix versus a defective one? Yeah, Turk? Not so much. Actually, this just has to do with whether the eigenvalues are pulling their weight or not in the sense of producing eigenvectors. It's really what it's coming down to. Yeah. But yeah, there's always the potential to make those kind of connections. You else have any questions so far? There is one that you should have. That's why I'm pausing, right?
Yes, yes.
I'm pausing to see if anybody has a question, because I know there's a question. If I was sitting in those desks right now and my professor had just gone through all this, I would have been thinking of a question. My question is, who in the world cares about whether a matrix is defective or not? Like, what's the point? There's a little bit of a hint in this alternative word, diagonalization or diagonalizable. And we're going to talk about that shortly. That when you have a non-defective matrix, i.e. a diagonalizable one, that is a good thing. That is something that is very helpful from a practical standpoint, particularly in probability and statistics, right? Which has, of course, a lot of real world applications. So I'm going to come back to that, but that's always a question to be asking. Like, why are we talking about this? Who cares if every eigenvalue pulls its weight or not? What's the big deal, right? So I am going to address that. Okay. Before I do that, though, guys, I do think I would like to do one more just straight example of finding the bases for the eigenspaces of a matrix. So I've written it down here. It's only a 2x2, and I'm going to call this matrix C, just so it doesn't get confused with the earlier matrices that we did earlier today. Okay. And this time we're going to add the extra question at the end, which is, let's decide if C is defective or non-defective. Okay. So let's practice one more of these, and then hopefully the mechanics of this will start to feel a little bit more comfortable. Okay. So as you guys know, the way we do this is we start off with our characteristic equation. So I take my matrix and I subtract lambda off of the main diagonal. So I leave the off diagonal values exactly the same, but I'm going to subtract lambda off of the main diagonal. Now, because this is only a 2x2 matrix, I don't really need to use cofactor expansion here like I was doing on those 3x3 examples. We can just use the little 2x2 determinant formula that you all know. So AD minus BC, right? So we'll get something that looks like this, I think. 2 minus lambda times 6 minus lambda, and then adding 13 to that. Okay? And this is just going to be a quadratic. So I'm just going to go ahead and multiply it out. There's nothing wrong with doing that in this case. So we get lambda squared, and then I have minus 2 lambda and minus 6 lambda, which actually makes minus 8 lambda. And then plus 12 and plus 13 makes plus 25. So this is the characteristic equation. And as we have learned how to do, we need to set that one equal to 0. Okay, so this is always the first step. And when we look at this, unlike the ones that I did earlier today, this one does not factor nicely. It doesn't mean that it doesn't factor. It just doesn't factor nicely. So guys, every polynomial always factors completely down if you allow roots to be anything. Okay, you always have to be able to, the words I always hate to hear out of a student's mouth is, it doesn't factor. That's not true. Everything factors, always. And when I'm sitting next to the math majors at graduation, since I'm the faculty marshal, I conveniently get to sit in the front row. And nobody can go across that stage unless they walk past me first. And so when I'm there with the math majors, I usually have to ask one last question. Let's make sure there wasn't some terrible mistake here made. And I'll ask them, does every polynomial admit a factorization into linear factors, and hopefully the math majors get that right and say, yes, you can always do that. So even if the roots are not nice, they do exist. Let's check this out. This one does not factor nicely. I'm going to use the quadratic formula to factor it and just get my lambda values. So this is negative b, which would be 8 plus or minus the square root of b squared, which is 64, minus 4ac, well, 4 times 25 is 100, all divided by 2. Okay, so these are going to be the lambda values. 8 divided by 2 is 4, and then plus or minus, oh, look at that. We have 64 minus 100, which is negative 36 underneath a radical. So it's a square root of a negative number, which means what is the square root of negative 36 going to be? It's going to be 6i. The imaginary number I, do you remember? So there's a little appendix in the book, at the very back of the book, that has a review of complex numbers. We're going to be needing that. We're going to be needing some basic complex numbers here. This is 6i, but of course I'm dividing it by 2, so that becomes 3i. So we get the roots of 4 plus or minus 3i. Okay? We have to live with that. It is what it is, right? If we get imaginary numbers. However, are we able already to decide whether this matrix is defective or not? Let's see. Non-defective means every eigenvalue pulls its weight. What are my eigenvalues here? Well, I have 4 plus 3i and I have 4 minus 3i. Are there any repeats? Do I see the same lambda twice? No, these are not the same number. There's no repeated lambdas, so of course, every eigenvalue can pull a weight of 1. So guys, we already know that this is not defective. And again, there's supposed to be something good about that, which I haven't explained yet. But I'm going to come back to that. This is a good thing. It is non-defective. So now let's go to our eigenspaces. So let's take the first eigenvalue, which is 4 plus 3i. So I'm just going to write the word non-defective here. We already know that. We already know that it's not defective. But what are the bases for the eigenspaces? I still want to work all that out. So to do that, I have to do this null space thing, right? The null space, give yourself plenty of room, guys, because now we've got imaginary numbers to worry about. Remember how we do? We take the eigenvalue and we subtract it from the main diagonal and make our null space out of that. So I have to subtract 4 plus 3i from the main diagonal of this matrix. What is that going to give me? If I take 2 and then I subtract 4 plus 3i, it's going to be negative 2 minus 3i, and then negative 13. And then on the second row, it's going to be a 1, and then a 2 minus 3i. Again, I just took 6 and I subtracted 4 plus 3i, the quantity of 4 plus 3i. So if I take 6 and I subtract the quantity of 4 plus 3i, I'll get 2 minus 3i. This is your matrix. Now, here's the deal. You're thinking, oh, the EROs are going to be horrendous. No, they aren't. No, they aren't. Let's remember that this matrix cannot be invertible. Can't be, because the determinant was set equal to 0 when we solved this problem. That means that if we did the EROs, one of these 2 rows would get zeroed out. Actually, what that means is that although it does not look like it, these 2 rows are actually multiples of each other. I know it would be so much more obvious if we had something like this. If I had rows that look like this, yeah, I just cross off the second row. It's just obvious that the second row is a multiple of the first row. These imaginary numbers are sort of camouflaging the fact that these rows actually are multiples of each other. If you multiply the second row through by negative 2 minus 3i, you'll actually get the first row. It may not be obvious, but you know what I'm going to do right now, guys? I'm going to trust the theory. I'm going to trust what I know, which is that this null space can't give me two pivots. I'm gonna cross off a row kind of without even thinking about it. Because I know I have to be able to. This matrix cannot be invertible. I must be able to cross off a row. It actually doesn't matter which one you cross off. I usually like to keep my pivot as a 1, so I will typically do that. But that is it. And now I need to come up with an eigenvector based on this second row. Now, I could set up a free variable. Okay, I'm going to show you the way that I'm not going to do the problem. I could set up my free variable here. Y is free, and then X is going to be some messy thing involving 2 minus 3i. I guess it would be -2 plus 3i times t, I believe, something like that. And then I would bust out my variable. That's fine. However, I showed you something last Thursday that gives you a much faster way to do this. Does anybody remember what I called it? Say it again.
The AB trick.
The A-B switch trick. Yes, that is exactly right. So guys, always read your notes before you come to class on Tuesdays and you'll have that stuff in your mind. Basically, you could just, without even taking a breath, write down the eigenvector. You switch these two entries and you do a sign change on one of them. I like to usually put the sign change on something that's easy. So I'll change the 1 to a -1. And that's my vector. So this is my basis for E sub lambda equals 4 plus 3i. That's it. That's going to be it. Okay? That good? Now, there's actually a little bit more good news about this, if I can find it. Yeah, so that's my first eigenspace. Notice, everybody notice that this eigenvalue did pull its weight. It's got imaginary numbers in it, but that's okay. It's still legit, right? My other eigenvalue, which is 4 minus 3i. So that's my other lambda. I have 2 lambdas here, right? This is also going to give me an eigenvector, but I have another little bit of good news for you, which is that if you've done all of the work for one of your complex values, the other complex number is actually just the so-called conjugate of the original complex number, right? So here we have like a plus bi, and this one is just simply a minus bi. It turns out that we can immediately write down the eigenvector for this one without doing another null space. And it's just the conjugate. I'm going to put a bar on this thing. So when I put a bar on a complex number, it just means that I'm switching the imaginary part of that number in terms of the sign. So 4 plus 3i, if that's lambda, then the conjugate of lambda is 4 minus 3i. And in order to write down the corresponding eigenvector, this is a nice little trick that saves you some time. You just take the eigenvector that you found before and you conjugate it. So don't do another null space because it just takes extra time that you don't need to do. Just take these two numbers, guys, and conjugate them. 2 minus 3i would turn into 2 plus 3i. Okay? And -1, when you conjugate a number that's already real, it actually doesn't change at all because the only thing you're changing is the sign of the imaginary part. That would be it. This would be it. This would be your basis. This is the basis for the eigenspace E sub lambda equals to 4 minus 3i. So I know it's a little weird notation. This is a vector with a bar on top of it. So you're just taking the original vector and conjugating all of its entries to get the corresponding eigenvector here. Now, if you don't like that, if you don't believe that, you can, of course, just do another null space and get an eigenvector that way. And as with everything in this class, when you're finding bases, they're not unique. What if the person next to you had crossed off this row instead of the top row? That would have been fine. And then that person would have been playing around with these two values, to make their vector using that A, B, switch trick thing. Right, so don't just expect there could only be one answer. It's definitely more than one. Okay? Any questions on that example? Maybe I should write this into the notes over here. So just as a quick little remark, because this is something you're gonna want to be able to look back and review. So if lambda and v is an E pair of complex values. So let me just say, let's just say that lambda is equal to A plus BI. And let's just say that the vector V looks like some real vector R plus I times some imaginary vector S. So if your eigenvalue eigenvector pair looks like this, then we also have another eigenpair. This is just a general fact. This will always be true. We'll always have another eigenpair, namely lambda bar and V bar. Right? And so this is where lambda bar is a minus BI and the V bar is R minus IS. So you're switching the sign of the imaginary part of the eigenvalue and eigenvector. It's just kind of a little something you have to memorize. Can you see that? If you need to stand up, go ahead. I just ran out of room over there. This is how it looks in practice, right? So my eigenvalue, eigenvector pairs, they always come in conjugates like this. The eigenvalues are always conjugate values. And so once you've done one of the null spaces, which I've done up here in the big circle, then for the other eigenpair, you just have to conjugate the eigenvalue and conjugate the eigenvector, and you get your basis for free. You don't have to do any extra work. Yeah. That's how that works. Okay. So far, so good. All right. I only have about 10 minutes. I'm going to spend 5 of them trying to show you why we should care about this, and then 5 of them taking a look at. There's really only one problem over there that's really a big deal from chapter 6. So I'll do that one. So why do we care about this? Let me just give you a quick intro to this right here. This is in section 7.3. And the word diagonalizable has shown up in our notes already. Remember, diagonalizable is just another word for non-defective. And when you have a non-defective matrix, right, let's set that up. The setup here, guys, is A, which is n by n, is a non-defective matrix. Right? So what is so great about this? Right? This would be the question. What is so wonderful about every eigenvalue pulling its weight? Or with there being n linearly independent eigenvectors for this matrix? What is the big deal about that? Well, I'm going to show you. It's actually a quick calculation. Let's consider n linearly independent eigenvectors. I'm going to label them as like v1 and v2 and dot, dot, dot up to vn, like so. Each of those eigenvectors has a corresponding eigenvalue. So let me list those kind of right next to the eigenvectors, the lambda 1, the lambda 2, all the way up to the lambda n like that. And so this is the setup in the case of a non-defective matrix. We're gonna have n linearly independent eigenvectors. Okay? And you can make all these pairs. Right? So here's what we're gonna do. We are going to, by the way, somebody way smarter than me figured this out. This is not me coming up with this, but I'm just the messenger. We're gonna form a new matrix S, and this one is also n by n. And the way we're gonna do that is we're gonna lay these vectors, these eigenvectors that we have hopefully calculated into the columns of S. We're gonna lay the eigenvectors vertically into the columns. Now, this is a square n by n matrix whose columns are Li. Does anybody remember if I have a square matrix whose columns are Li, what would be something that's true about that matrix? Louder? It's invertible, right? It's an invertible matrix. This is exactly right. Let's just note that S is invertible. Awesome to know that. S is invertible. And then I'm just gonna do something kind of weird. Again, I didn't figure this out, but I'm just gonna show you. What happens if we actually take A times S? The original matrix A being multiplied by this matrix whose columns are the eigenvectors that we calculated for A. Well, let's just write out the matrix S in terms of these columns again. So my first step is just going to be to do that. And guys, the way that you do this multiplication is you go across, you take dot products of the rows of A with these columns. So like if I want to figure out the first column of the product here, you're simply going to be taking A and multiplying it by V1. And what is A times V1? Well, let's first just write that down. A V1 and then A V2 and dot 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 up to A Vn. Let's just recognize that that's ultimately what you're going to end up with. And what is A times V1?
Lambda 1 to B1.
Lambda 1 V1. The most important equation in chapter 7 is that AV equals lambda V. Exactly. So AV1 turns into lambda 1 V1. And AV2 turns into lambda 2 V2 and dot 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 dot. AVN turns into lambda n Vn. That's it. Well, guys, this matrix is actually the same matrix as S was, except with each column being scalar multiplied by the appropriate lambda value. You can actually achieve that. You can actually achieve that in a different way. I'm going to write it down and then we'll look at it and make sure you guys believe it. We can take the original matrix, and if I want to swell up the columns by these lambda scalars, all I have to do, my friends, is multiply on the right by a diagonal. It's this word. A diagonal matrix that has these lambdas going all the way down the diagonal. Yeah. Has anybody ever tried something like that? If you just took any old random matrix here, guys, this is not part of the notes. I just want to put this over here for you. If I multiply any random matrix on the right by this kind of a diagonal matrix, and I do my matrix multiplication dot product style, what I end up getting is 2A, 5B, and 2C and 5D. The columns of the original matrix get multiplied by the 2 and the 5. And that's what's going on here. These are the diagonal values that are multiplying the columns of this original matrix. Guys, this is nothing more than S times D, where, let me write down what D is. Right, where D is simply the diagonal matrix that has these lambdas going down the diagonals. And so I've only got a couple minutes, but I'm just going to basically give you the summary of what I just showed. I started with AS and I ended up with SD. Can I cancel those S's? If that was possible, if I was allowed to cancel the S's, I would then be saying that A is equal to this matrix, which isn't true, right? A is just some other random matrix. I'm not going to cancel those S's. However, I'm going to use the fact that S is invertible to allow myself to reorganize this a little bit into a different form. Namely, I'm going to put an S inverse on the left of both sides. And of course, the S inverse times S would be equal to D. Sorry, the S inverse times S would be equal to the identity matrix, which then gives me D. So you see, you cannot cancel the S and the S inverse unless they're right next to each other. If the S and the S inverse are right next to each other, I could have canceled them, but they're not. They're separated by A. By the way, if we wanted, we could do this the other way around. I could solve for A by putting the S inverse on the right side. Any of these are simply legal rearrangements of each other, and they're totally, totally good. You will have to memorize, and I'll come back on Wednesday or on Thursday and write this down again. You got to remember which side the S inverse goes on, which side the S goes on. But what we have done here, my friends, is we have diagonalized the matrix A. We have basically said, oh, I can write A in terms of a diagonal matrix, namely this matrix, which just has the lambdas on the main diagonal. I still don't think you're convinced that this is a worthy objective. At least I wouldn't be convinced. Like, what is so great about being able to write your matrix like this? So I'll have to save that as my cliffhanger for Thursday. I will explain it. As far as anything else for today, I put a little hint on problem 29 on the board there. The problem 29 on section 6.4 is literally going to take you 20 seconds to do. It's super, 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 super fast. You just need to write down the form of a 4x4 upper triangular matrix and figure out how many slots that would take. However, the one problem that's on that board that I did not do, and which is a really good problem, is number 43. So what I am going to do is I am going to send you a video of how to do that problem. That one I have put on my exams before. It is so good as a nice exercise. So I will, I'll make sure that I give you a video with that little problem. I'll send it to you later today. Thanks, guys. Appreciate you being here. Let's sign this thing off.